Yeah. All right, guys. Questions over the homework? Yes. Yes. I know about as much as he does. We're going to the conference too, Spark. I know that I will be there with y'all. I will be out there with y'all. Do not know.
Just showing up to work.
Yep.
I'm going to Niagara Falls. You don't know, he just works here.
Yeah. So what we're doing today is solving. So what we're doing today is we're starting the section over solving radicals, 5.4. And the first core concept we have is squaring each side of a equation. If two expressions are equal, then their squares are also equal. Not a whole lot there. Let's look at solving this one here. So we have several main steps. Write the steps above it. I wouldn't write it necessarily next to it because we have a problem there. First main step in solving radical equations. Is there one radical? So if we look at this first problem here, square root of x plus 5 equals 13. Is there one radical? Yes. If so, get it by itself. If not, even them out. If so, get it by itself. If not, even them out. So as we look at this first one here, square root of x plus 5 equals 13. There is one radical. So we need to get it by itself. So the first thing we can do to get this radical by itself is subtract 5 from both sides, because our 5 minus 5 would be 0, telling us the square root of x is equal to 8. Questions on this so far? Is the radical by itself? Yeah, and at this point, we don't care so much what's inside the radical. We just want whatever the radical is by itself. Once we get it by itself, put both sides to the nth power. Because the goal at this point is to get that square root to go away. So what power are we going to put both sides to? 2. Because the square root in square, if I square that side, square root and square would cancel, leaving us with x. And what we do to one side, we're going to have to do to the other. Square root of x squared is going to be x. 8 squared is going to be 64. So we finished step 3. Step 2. Any questions on steps 1 or 2? We ready for step number 3? Are there any radicals left? If so, repeat steps 1 and 2. If not, solve for the variable, check. For the most part, we won't need to check our answer. The main cases where we would need to check it or make sure that the solutions work is when the variable shows up outside of the radical also. Because we cannot take an even root of a negative number. Odd roots, that's perfectly fine. It doesn't matter. Even roots, I cannot take the square root of negative 64. I can take the square root of 64, but not negative 64. Okay, so step 3, we're good. Step 4, solve for x. It's solved for, yes? X is equal to 64. And if we wanted to check it, we could just grab the calculator and say square root of 64 plus 5 is, Indeed 13. Both sides are equal, so questions on this here. 3 minus the square root of x is equal to 0. Is there more than one radical? No, so we need to get it by itself. So what can we do first? What do you think? Yeah, we can minus 3. We can subtract 3 from both sides. You know, it'll tell us that negative square root of x is equal to negative 3. Is the radical by itself? No, so what do we need to do? Divide by negative 1. Because negative square root of x divided by negative 1 would be positive square root of x. Negative 3 divided by negative 1 is 3. Now is the radical by itself? Yes? So we're going to move on to our next step, step 2. We're going to put both sides to the nth power, and that power would be 2. Square root of x squared would cancel, leaving us with x equals 9. There are no radicals left. X is already solved, so x is equal to 9. Questions on this here? Square root of x equals 6. Is there one radical? Get it by itself. Put both sides to the nth power. So we're going to square both sides. Square and square cancel, telling us x is equal to 36. There are no radicals left. It is by itself. So x equals 36. We have one radical. Is it by itself? Well, no. What do we need to do? Add 7 to both sides. Negative 7 plus 7 is 0, telling us that the square root of x is equal to 10. What do we do next? Put it to the nth power, and that nth power is 2. Square and square would cancel, telling us x is equal to questions on this here? I think we're good there. Let's look at this one. 4 times square root of x plus 2 plus 3 equals 19. Is the radical, well, we have one radical. Is it by itself? No. What do we need to do first? We need to subtract the 3. Four times square root of x plus 2 equals 16. Is it by itself? No. So what do we need to do? Divide by 4. 4 divided by 4 is 1, leaving us with the square root of x plus 2 is equal to 4. Is the radical by itself? Yeah, so we're going to put both sides to the nth power, and that power would be 2. And the reason this works out nicely, because the radical is by itself, that square root and square will cancel. We don't have to do anything to it. If I had something added to that square root, we would actually have to multiply it out. We'd actually have to distribute. Square both sides, so the square root of x plus 2 is x plus 2. 4 squared is 16. Do we have any radicals left? No. Solve for x. So we would minus 2 minus x is equal to 14. And if I wanted to check it, 4 times the square root of 14 plus 2 plus 3, if I can grab a calculator, say 4 square root of 14 plus 2 plus 3, and see if that gave me 19. It does. It works. All right. What would we do first? We need to get the radical by itself since we just have 1. And that'll tell us 3 times the square root of x plus 5 is equal to 12. What would we do next? Divide both sides by 3. Going us at the square root of x plus 5 is equal to 4. Then we would put both sides to the nth power, in this case power of 2. Square root and square would cancel, telling me that x plus 5 is equal to 16. Do we have any radicals left? No. So we're going to do what? Minus 5 from both sides and get that x is equal to 21. Hopefully not 11. 16 minus 5. Questions on this here? Questions on any of this so far? I think we feel pretty comfortable with this here, yes? Yep. Because here we would subtract 7, get 4, square it to get 16 minus 4 and get 12. And even here, I don't think it's going to be that much different. I think it should be 30. I don't necessarily feel like we need to do more here. Solve. Square root of 2x minus 1 is equal to square root of x plus 4. Is there one radical? We got 2, so we need to even them out. And all that means is we want to try to get an even number on both sides. Since I have 2, evening them out means I really want 1 on either side. If we had 3, we'd really have to pick how we want to do it, 2 on one or the other. If we had 4 radicals, we'd try to get 2 and 2. 5, we're going to do 3 and 2. We try to even them out so we have the same number on both sides. Here, we only have 2, so we're going to do 1 and 1. So they are evened out, yes? So that means I move on to step 2. I'm going to rewrite it for my own sake. We're going to put both sides to the nth power. And really, in this case, we pick one of the sides to try to get it to simplify as far as possible. I'm going to pick the left-hand side. If I want this one radical to simplify, we'd put it to what power? 2, yes? Because on the left side, if I square it, the square and second power would cancel. But what I do to one side, I have to do to the other. Well, the left-hand side is a single square root, nothing else being added, so the square root and square would cancel, yes? So what that tells me is that 2x minus 1 is equal to x plus 4. Questions on this here? So we finished step 2, step 3. Are there any radicals left? Solve for x. Solve for the variable. What can we do first? Minus x, yes. 2x minus x is x. So we get x minus 1 is equal to 4. Then we would plus 1. X is equal to. If I wanted to check it, we don't have to. We're saying that 2 times 5 minus 1 should have the same value as 5 plus 4. I'm going to check the left-hand side first. 2 times 5 would give me 10. 10 minus 1 is 9. Square root of 9 is 3. Do the same thing to the left-hand side. We'd have 5 plus 4 is 9. Square root of 9 is 3. Both sides do have the same value, so it works. Look at the next one. We have more than one radical, so we need to even them out. Are they evened out? Yeah. We can put both sides to the nth power. Because we don't have something being added to those radicals or more than one term, they will simplify out, telling us that 4x minus 3 is equal to x plus 9. So what can we do next? Well, we could add 3, we could subtract 9, we could subtract 4x. It doesn't really matter. So if we want to subtract x first, that's fine. 4x minus x is 3x. Minus 3 is equal to 9. But once we do that first one, it kind of tells us what the next steps have to be, or should be. We add 3, telling us 3x is equal to 12. Divide by 3, so x is equal to 4. We agree? We ready for the next one? So, let's look at the next problem. Again, just like the last two, there's more than one radical, yes? So we need to even them out and we're good. They're already evened out, yes? Now, how many do we have on one side? 2. We have 0 on the other side. Now, the reason I say to even it out, I would not write this, is that if we jump straight into step 2, it's not going to make a big well, it will not change the solution. Let me put it that way. It will not change the solution that we get. But by squaring this left-hand side, and because of that subtraction, it's saying we're multiplying this term by itself. We would actually have to distribute this whole thing out, multiply it all the way out. I'm not going to walk that through, at least this hour. If you want to see that walkthrough, I did it last hour. It changes this problem significantly, at least in steps. The solution's still the same, but the first thing I would want to do is move that radical to the other side. And as we saw yesterday, well, if I add the square root of 4x minus 7 to both sides, on the left-hand side, the negative square root of 4x minus 7 and the positive 4x plus minus 7 are like terms. So I have negative 1 plus 1, which gives me 0, telling me that the left-hand side now is the square root of 3x plus 1. The right-hand side is now 4x minus 7. So we have them evened out, which means we can put both sides to the nth power, and that power is 2. Since we only have one term on the left-hand side, we're multiplying it by itself, which would cause that square root and square to cancel, telling me that we have 3x plus 1 is equal to 4x minus 7. What do we want to do first? 3x minus 3x would be 0, telling us 1 is equal to x minus 7. Then what do we do? Plus 7, add 7, telling us x is equal to. Questions on this here? Do we feel comfortable with these here? It'd be 1/4, by the way. Is that what you got? Yep. This one here has a cubic. We have a cubed root, yes? And again, like most things in a lot of different areas, we learn a method that works, and then we encounter a new radical, a cubed root instead of a square root, and most of the time we've got to learn a new method to do this here. Well, let's apply the method that we've been using up to this point. Step number 1 says, is there more than one radical? No, so there's only one, get it by itself. Luckily for us, it is. Step 2 said to put both sides to the second power, yes? No, what did it actually say? We put both sides to the nth power, yes? So now we're not putting it to the second, we're going to put it to the third. And it might have seemed odd up to this point why I said nth power instead of squared, and that's because it doesn't matter what the root is. If we put it to a power that matches that root, that cubed root and third power, since it's by itself, will simplify out, telling us that 5x minus 2 is equal to, well, 12 to the second, 12 squared is 144. 12 cubed is 1,728. Are there any radicals left? No. So we need to solve. So we're going to add 2 to both sides, telling us that 5x is equal to 1,730. Lastly, we would divide by 5. 3 would give us 15, so 23, 4, 6, 1730 divided by 5. 346. That's it. Questions on this here? Really, are these cubics any harder than what we've been doing? No, they're the same thing, but we're dealing with cubed roots instead of square roots. It really doesn't matter. We can have 4th roots, 5th roots, 6th roots. We can make the root as big as we want. The process does not change. And that is 15 problems. It does look like it is a lot more than that, but 3 through 7 odd, 11 through 17 odd, 27, 29, 33, 34, 37 through 43 odd. I have a feeling you can get most, if not almost all of this done before the bell. You can probably get number 3 done very quickly.